Welcome to part two of our video series on estimation. In this video, we are going to do some review in order to prepare us for confidence intervals. Okay, specifically, we're going to review the Z distribution, and within that review, we're going to cover or review simple math under the Z curve that is driven by symmetry. We're going to review standardization of the sample average, which I also call X bar, and we are also going to review use of the Z probability table. In addition, we are also going to review the T distribution and use of the T probability table. I'm Renee Clark from the Swanson School of Engineering at the University of Pittsburgh. Okay, so let's first review the Z curve or the Z distribution. Okay, if I define Z sub alpha over 2 as the Z value having an area of alpha over 2 to the right. So if I point that out, okay, and notice how that area right in there is an area of alpha over 2, okay? Then via symmetry, okay, we know that there is a value of Z that sits along the x-axis having a value of alpha over 2 to the left, okay? So via symmetry, the opposite of Z of alpha over 2, which is a negative value because it is to the left of 0, has area of alpha over 2 to the left. Okay, so minus Z of alpha over 2 has an area of alpha over 2 to the left. Okay, so let's do an example of this. Okay, draw a picture. It helps a lot. Okay, this is the Z curve. Okay, if you use the probability table for Z, you can determine that a Z value of 1.51 has an area of 0.0655 to the right, okay? By symmetry, we therefore know that the value of Z negative 1.51 has that same area of 0.0655 to the left. Okay. Okay. Let me direct your attention back up to the first picture. The area in between minus Z of alpha over 2, which is right there, and Z of alpha over 2, which is right there, okay? That area is equal to the following, keeping in mind that the total area under that curve is equal to 1, okay? So the area under the curve in between those two values is 1 minus, okay, the area that's to the left of the negative value, which is alpha over 2, plus the area that is to the right of positive Z of alpha over 2, which is also alpha over 2. Okay, so that simplifies to 1 minus alpha. Okay, so what this is saying is that the area under the curve in between those two values of Z, which is shaded in blue, and I'm going to re-highlight it here, this area that I am outlining here is equal to 1 minus alpha, just as shown in the picture. Okay, so that area equates to the blue area under the curve. Okay, next topic we want to review is how to transform a normally distributed sample average, or X bar. Okay, so the first thing we want to review are the parameters of X bar, or the parameters of the sampling distribution. distribution of x bar. Okay, these are shown here. Okay, so the mean or the expected value of x bar, which is written as mu x bar, is mu. Remember, it is equal to the mean of x. Okay, the variance of x bar, written like this, is actually sigma squared over n. Remember that the variance for x bar is always less than that for x by a factor of n. In other words, we divide by n in the denominator. Okay? The standard deviation then is simply the square root of the variance. So if we take the square root of this, we will get sigma over the square root of n. So that is the standard deviation of x bar. Okay, so these are your parameters of x bar, or the parameters of the sampling distribution. Okay, so in order then to standardize x bar, we're simply going to subtract off its mean, right, which is right there. Okay, and we are going to divide by its standard deviation, which is right there. Sigma over the square root of n. So that is how we standardize x bar. Okay, now in order to standardize x bar, we know that it must be normally distributed in order to standardize it to a z random variable. Okay, the question is, under what two conditions will x bar be normal? Okay, these are the two, either one or both. If either one or both is true, x bar will be normally distributed. Okay, the first condition is if your parent population of x is distributed normally or normally distributed, then automatically x bar will be distributed normally. Okay, the second condition is if your sample size greater than or equal to 30, then due to the central limit theorem, x bar would be normally distributed. Okay, so if either of these two conditions is true, or if both of them is true, then we know x bar will be normally distributed. Either your parent population is normal, or your sample size is sufficiently large, greater than or equal to 30. Okay, if either of those or both is true, then that's how we know x bar normally distributed, in which case we can standardize it to be a z value, okay, and use the z tables in the back of the book. Okay, so this is a review of the areas under the standard normal curve, which are found in the back of the book. Okay, so these are values of z. Okay, z is formed by the combination of the row headings and the column headings, and in the center of the table are areas or probabilities under the normal curve. Okay, so for example, let's say we wanted to find a certain z value such that it has an area of, say, alpha over 2 or 0.0495 to the right. So we want to find a value of z such that it has an area of 0.0495 to the right. Okay. How do we do that using the table? Okay. Remember that the visual legend isn't shown here, but in the table in the back of the book, it provides z values such that the areas in the center here are to the left. Okay, so if we want to find the z value such that it has 0.0495 to the right, then we need to read off the z value that has an area of 1 minus that to the left. Okay, and that happens to be when you subtract 0.0495 from 1, you get 0.9505. Okay, Okay, that's area to the left. And that's what these areas are in the back of your book. Okay, so basically we have to read off the z-value such that 0.9505 to the left. And we simply do that by going into the table and finding the z-value that has 0.9505 to the left. That z-value is 1.65. Okay, so our z-value in this case, the final answer is 1.65. That's the z-value there. Okay, let's review the t-distribution. Okay, you recall that t is defined as the following. Okay, it looks similar to z, except that instead of sigma in the denominator, we have s in the denominator, which is your sample standard deviation. Okay, so t is defined as x bar less mu over s over the square root of n. Okay, in order to use the t-distribution, x, or your parent population, must be normally distributed. Okay, there is no concept of the central limit theorem with t. The central limit theorem does not relate to the t-distribution. Okay, and you'll recall that t has nu, or n minus 1, sample size minus 1, degrees of freedom. Okay, this is a review of the t-table in the back of the book. Okay, and this is where we get values of t. Let's do a little review on this one. What is the value of t having an area of alpha equal 0.025 to the right for a sample size of 15? Now, the visual legend is shown here, okay? And the alpha values that you read out of this table by the visual legend are areas to the right, okay? And we are looking for alpha of 0.025 to the right. Okay, so it's a simple matter of just reading straight out of this table. Sample size is 15. That means nu, or degrees of freedom, 14. Okay, so we are going to read off the t-value that falls at the intersection of 14 degrees of freedom, having an area of 0.025 to the right. Okay, that t-value happens to be at the intersection 2.145. Okay, so our t-value of 0.025 comma 14 equals 2.145. Okay. We wish to thank the National Science Foundation under Grant 233-5802 for supporting our work. Thank you for watching.